This is going to be our first look, at a non-STP gas. And so up to this point, when we've been reading these problems, we always see STP or standard temperature and pressure. But as we read this one, it looks a little bit different here. So it's still asking us for volume, liters, and it tells us that this time we have a temperature of 35 degrees Celsius, we have a pressure of 0.980 atm, and then we're given a mass of tungsten oxide. And I realize we don't use tungsten oxide that often, and so let me write that chemical formula out there below. And all I've done here on the front end is write down the information that's given to us. And then, of course, we also have that mass, which is 875 grams of tungsten oxide. And so how can we calculate the volume? Well, this is where a lot of times students will see that balanced chemical reaction, and so then they make the assumption that they automatically need to start into a stoichiometry problem. But if you look at this, we cannot use 22.4 liters. We can't use that 1 mole equals 22.4 liters. And why can I not do that? Because it's not at STP. So the first thing that we need to do is to figure out moles of this, okay? And so what we are going to do is back up a little bit here, and we are actually looking for liters of hydrogen gas. So not only that, we're looking for liters of H2. So before we can do that, we've got to turn 875 grams of tungsten oxide into, grams, or if we wanted to do moles, we'll go ahead and turn 875 grams of tungsten oxide, and ultimately what we want here are moles of hydrogen, because we have to have a value for N in that PV equals nRT. Okay, if we're trying to solve for volume, then we need a value for pressure, moles, and temperature, and the only value we don't have right now is that N value. Why do I have to change it out right now? That value is given to you in tungsten oxide, and we want it to be in hydrogen, which means we've got to make that N representative of hydrogen. So let's go ahead and back up to Unit 7 where we've been, and let's do a little stoichiometry. First step is to get rid of grams of tungsten oxide, which is what we're going to do right here. We have to figure out what value goes right here. Well, here's where that molar mass is going to come in. Tungsten weighs 183.84 grams. And then, of course, we've got oxygen, who weighs 16 times 3 would give us 48 total. I'm going to put that in the calculator because I don't trust myself. Getting 231.8 grams. And again, think about what that represents. And now we're going to drop down moles of tungsten oxide, and I'm going to erase that. And here's where we're going to end up having that mole to mole ratio, where now all we need to do is see that 3 in front of the hydrogen, and then in front of the tungsten oxide, I don't see anything, so I make the assumption that it's a 1, and we are going to multiply straight across. Whoops. And get 11.3 moles of hydrogen. Okay, so that's step 1. Now that we have that value, we can use our ideal gas law. We know, as stated earlier here, that the pressure is 0.980, and that value was given to us in atmospheres. I'm trying to solve for volume, so I don't know what V is. I know that N is 11.3. Remember, that represents moles. R is that universal gas constant, and so this is where we've got to look back at our pressure, and we see that it's an atm, which means we're going to use the constant 0.0821 times the temperature was originally given to us in degrees Celsius, but remember we have to change that into Kelvin, and when you add 273 to 35, you get 308 Kelvin. And now it becomes an algebra problem for us. So we're going to combine like terms right here and multiply 11.3 times 0.0821 times 308. We're going to divide that by 0.980. And we're going to get 291.6. So we'll run that to 292 liters. And again, that's of hydrogen gas. These non-STP problems can seem a little overwhelming at first, but again, it's taking things that you're already working with and putting multiple steps together.